So from general metrics into L2, of course this is small l. This is small l. Big L is different things. And we have distortion C. From weighted trees to LP, we have order of distortion of order of C. We have unweighted trees. We can map into trees with order of C. We can map into R1. We can map into ultrametrics. Ultrametrics is used in bioinformatics and genetics and protein folding, and many of those applications are inspired by biology. So, of course, in machine learning, it becomes very restrictive. If one cares only about ultrametrics, it's a very restrictive construction and space. And maybe it is more useful and more general to work on LP spaces rather than ultrametrics. But at least we can use the inspirations, because ultrametrics, it reminds me of fractals. For example, so we can have a distortion into some distortion, and the ultrametrics, the difference between, it is instead of triangular inequality, we have something else. So the distance between x and y is less than maximum of distance between x and z and distance between z and y. In triangular inequality, we had something, and now it is replaced by this. So you see, the list goes on, because the research is growing, especially by researchers in Israel. They are actively working on that. About 20 people, 20 researchers are actively working on that. And so what I mean by distortion C, it means that the distance between f of x and f of y is less than C, distance between x and y, and distance between x and y. When C is equal to 1, it's isometric, and the minimum interpoint distance between points is 1. The maximum interpoint distance between them is delta, which we call it spread. Delta is spread. So for example, you see these are, for example, this is the minimum, and the maximum is between P and P2. Maximum distance between P and P2. We construct an embedding with distortion. We want to focus on embedding into R1. We first start by this, because this is the easiest way to do that. We construct an embedding with distortion order of delta to 4, 5 and C 13, 5. For unweighted graph in 2005, M. Badoui, approximation algorithm for low distortion embedding into low dimensional spaces. So I'm just review that 2005 article. So we want to embed X and D we want to see embedded into R. So the approximation algorithm for low distortion embeddings into low dimensional spaces is that we I mean, metric embedding in ML started by multidimensional scaling literature. There are very few theoretical results. That's why they could not develop it more in the context of machine learning. And we use the shortest path metric, and we want to find f from V to R that is non-contracting. What I mean? It means that f of u minus f of v is greater than d of u and v for any u and v. So it minimizes the distortion C of m and f, maximum of f of u, f of v, d of u and v. So the goal is to find C line of m, minimum of C line of m and f for any f. Minimum spanning tree, we ordering the metric nodes using MST is a popular heuristic. So I want to summarize the result by the heart of that, which is the lemma, which says any short path metric over an unweighted graph G can be embedded into a line with distortion at most 2n minus 1 and in time order of cardinality of V plus cardinality of E. So the intuition is very similar because we are using Euler-Tur. Since the resulting graph is Eulerian, we can consider an Euler-Tur in C. For example, let's say we have this is U, this is V, this is W, this is X, U, Y, U, Z. And the weights are, this is 3, 5, for example, 1, 2, 4, 2, and this is, for example, 6. This is 4, and something like this. I mean, we label them like this. So a tour can be themed like this. For example, 1, 2, 6, 6, 2, 4, 4, 1, 3, 3, 5, 5, 1. So this is 1, this is 2, this goes to 3, this goes, so I'm counting them. So I'm assigning a value in R. This is my 6, this is my 7s, and this goes until 13. So we have a length of 2n. So since the resulting graph is Eulerian, we can consider an Euler-Tur. So starting from arbitrary node, we embed the nodes in T according to the order that they appear in C. So we ignored multiple appearance of a node, and we preserve the distance in C. So as you see, it is clearly the resulting embedding is non-contracting, since C has length 2n and the distortion is at most 2n minus 1. For example, distance between U and Z is 1. But what is the distance between f of U and f of Z is, in a Eulerian tour, if you count it and you label it, it becomes 11 minus 1, which is 10. So it is non-contracting. So what is the algorithm for computing an embedding of distortion at most order of c squared? We partition like this. We have V1, then in the partition 2, we have V2, partition 3, and this continues until PL. So the algorithm for computing the embedding is like this. First, we let f of opt be the optimal embedding. Of course, we don't know it, but we guess the nodes. We can always guess the nodes T1 and T2 such that f of optimal of T1 is the minimum of f of opt of V, and f of opt of optimal of T2 is the maximum of f of opt of V. So the second step is the compute shortest path P from V1 to VL. So from T1 to T2. And we partition V into disjoint sets, V1 to VL, V1, V2, V3, VL, such that for any U in VI, the distance between U and VI is the minimum of a distance between U and Vj, where J between L and 1, we have L partitions. And so this was the third step. And the fourth step is that for I is equal to 1 to L, compute the spanning tree Ti of the subgraph induced by those VIs rooted at VI. We embed the nodes of VI in the lemma that I told you that we used the Euler tour, and we're leaving a space of length VI between the nodes of VI and VI plus 1. So we embed the nodes here. So we have different Euler tours, but in a different spaces. So in this way, we are embedding it into R. And this is the real line. So that's the construction of embedding into real line. And so I just want to say another lemma, that the distance between VI and X for any X is less than C over 2. So the lemma that I will prove is that for every I between L and 1, and for every X in VI, we have the distance between VI and X is less than C over 2. So the proof is very simple. We prove it by contradiction. So we assume that there exists VI and Xi in VI such that dx and VI is greater than C over 2. We consider the optimal embedding. So by the fact that V1 and VL are the leftmost and rightmost embedded nodes in the embedding, it follows that there exists J, where J is between 1 and L, such that f opt of X lies between f opt of Vj plus 1 and f opt of Vj. Since x is inside Vi, we have f of Vj plus 1 minus f opt Vj. This one is equal to f of Vj plus 1 minus f opt x plus f opt x. I'm just adding and subtracting this value. Minus f of Vj. But you know that this one is greater than distance between Vj plus 1 and x plus the x and Vj. And this is greater than 2d x and Vi. And because this is greater than c, we have contradiction, because expansion of f is at most c. You cannot say that this is greater than c. So it's a contradiction, and we've proved that by contradiction. And there is a lemma that says for every I between L minus C plus 1 and 1, we have Vj is less than 2c squared. So the proof is as follows. We assume that there exists an I such that Vj is greater than 2c squared. Note that because the maximum of f of Vj1 minus f opt Vj2 is less than equal to c by c minus 1, and moreover, we can say that since j from I to I plus c minus 1 of Vj is greater than 2c squared, we have the maximum over any u and v inside the union of j from I to I plus c minus 1 of Vj of f of u minus f of w is greater than 2c squared. And then it follows that there exists u in VL for some L, that difference between them, f of VL minus f of u, is greater than equal to 2c squared minus c, which is greater than c squared over 2. And since the expansion is at most c, we have the distance between VL and u is greater than c over 2. And this is a contradiction with previous lemma that I have proved. I have proved this one. This is the less than that one, and this is the contradiction. And the final lemma that I should say for embedding any metric space into R is that the embedding computed by that algorithm that I say is non-contracting. So the proof is as follows. So let x and y be some vertices, and if x and y are in the same set, Vi, then clearly f of x minus f of y, the distance between them, is greater than distance between x and y. So this is one case. Okay, since the distance between x and y produced by a traversal of the spanning tree of the graph induced by Vi, it is at least the distance of x and y on that spanning tree. So which is at least d of x and y. Assume that